This is lecture 20, Kinetic Molecular Theory. In this lecture, we'll start to talk about gases and the motions of molecules. This will lead us into more complex discussion of molecules moving and interacting with one another. But the goal of kinetic molecular theory is just to take the motion of gas molecules and convert that into macroscopic gas behaviors. So we're taking something small, using it to get something big. So this theory requires 5 assumptions, or it was developed using 5 assumptions. Some of those assumptions are good, some of them are not so good. So let's go through them. First assumption is actually very good. It is that the volumes of molecules and particles of gas are very small compared to their container. So if these gas particles or molecules have sizes on the order of angstroms, and their containers are a 2-liter container or a whole room, then the container obviously has a much larger volume than the molecules themselves. So this is actually a very good assumption. The next assumption is pretty good as well. And in this assumption, it's just that gas molecules move at random and are constantly moving. So here I have a graphic just depicting a simulation I ran of gas molecules moving and bouncing around. And so they're all kind of randomly moving and moving continuously. The next assumption is an okay assumption, but not a perfect one. And that is that these gas molecules collide elastically. That includes bouncing off walls and bouncing off each other. Now, what elastically means is that all of our kinetic energy stays kinetic energy. None of it is converted into potential energy. In real life, some of the collision energy can be converted into potential energy. It can excite electrons inside of these molecules and so forth. But we're going to pretend that all these collisions just result in the acceleration of one particle and the deacceleration of another. So in other words, it's always just a transfer of kinetic energy. The fourth assumption is not very good. It's actually very bad, but we're still going to use it for this theory. The fourth assumption is that the molecules have no intermolecular interactions. Whereas we know already that molecules can be polar, and 2 polar molecules can see each other. One of them is going to have a partial positive end that's going to see the partial negative end on the other, and vice versa. So if these have charges on them at all, even if it's a partial charge, they're going to be attracted to each other, even through space. And the last assumption is another good one, and that is that the average kinetic energy is proportional to temperature. So it's not the kinetic energy of one individual molecule, but it's the average kinetic energy of all of the molecules gives us temperature, what we measure at macroscopic scale. So let's explore this idea a bit further. So we said the gas molecules are moving and are constantly moving in a random motion. So you have some that are going left, some that are going right, some that are going up, down, forward, back, etc., and combinations of those different directions. And so the temperature then is that we feel is basically an average of the energy with which the molecules are moving around in that random motion. So our temperature is proportional to our average kinetic energy. Now that word average there is actually really important, because if we look at gas molecules, so here I have another simulation where on the left I have hot molecules and on the right I have cold molecules. And what you'll notice is that on the left the molecules are in general moving more quickly, or on the right they're generally moving more slowly. However, if you watch those closely, even on the left in the hot molecules, you can find a molecule or two that's actually moving very slowly. And on the right, in the cold molecules, you can occasionally find a molecule that's moving very quickly. The idea here is that these molecules have a range of kinetic energies, and so we're just looking at the average to feel our temperature. And through further studies, scientists have been able to improve this equation. So they've gotten rid of this proportionality symbol and replaced it with this equals 3/2 RT here. So this R is a constant that we'll talk about in a little bit. So individual molecules don't have the same kinetic energy or speed, and that's going to be important in our next step. So our next step is going to be replacing the left side of this average kinetic energy, with a more detailed expression. So that more detailed expression, we've already seen the equation for kinetic energy, or one very common equation, which is 1/2 mv squared, which is 1/2 times the mass times the velocity squared. But in this case, we can't actually use velocity, or we don't want to use velocity. And the reason for that is that velocity is what we call a vector value. A vector means that it's not only a speed, but a speed in a certain direction. So if we defined a positive vector as moving to the right and a negative vector as moving to the left, then our velocity could actually be 3 meters per second or -3 meters per second. So if we take an average velocity of a bunch of gas molecules moving around at random, then our average velocity is always going to be 0, or really close to 0. What we want to do is get rid of that vector thing and just talk about the speed of these, the magnitude of the speed, or the magnitude of the velocity here. And so by doing that, now, if we're talking about speed, moving to the right at 3 meters per second is going to be a positive number, and moving to the left at 3 meters per second is also a positive number. So we're going to replace that v in this 1/2 mv squared with a u. The u stands for our speed. And this is going to be our RMS speed. We'll look at what that actually means on the next slide. But usually we want to solve this big equation right here for our RMS speed. So when we do that, we're going to move some things around. We're going to get this equation, where our RMS speed is equal to the square root of 3RT over m. What is this m? Well, that is actually our mass in here. Why is it capitalized? Well, there's a special reason for that, and I'll go over that on the next slide as well. So let's start, though, with the root mean, or the RMS speed. So RMS is an abbreviation that stands for root mean square. So the root mean square is calculated like this. It's a type of an average. It's not the typical average, the typical mean that we deal with. So in the root mean square, we're actually going to do these mathematical operations in reverse order. We're actually going to start by squaring something, and then take the average of those squared numbers, and then we're going to take the square root of that average. So this equation is how we actually calculate our RMS speed. So we take the speed of each individual molecule. So U1 would be the speed of molecule 1, U2 of molecule 2, U3 is the speed of molecule 3. Then we're going to square each of these before adding them together. So we square the first speed, second speed, third speed, and then we add those up and divide by the number of speeds we have. So we're taking the square, or we're finding the square of each of these numbers first, then we're taking the mean of the squares, and then once we do that, we take the square root. That's why I say we do it in reverse order of this RMS thing. We do the square, then the mean, and then the root. All right, so that is our root mean square speed. It's not exactly an average. And like we said, it's equal to the square root of 3RT over m. Let's talk about these terms a little more specifically in here. Or as a new constant we'll be dealing with, it's called the gas constant, and it has a value of 8.314 joules per mole Kelvin. The temperature then, or the T is then the temperature in Kelvin. We need it in Kelvin, so it can cancel out with that K in the R. And then our mass, our M, is going to be our molar mass, so the molecular weight of whatever gas we're talking about. But it's capitalized here to indicate that it's going to be in kilograms per mole. So usually we talk about molecular weight or molar mass in terms of grams per mole, but in this equation specifically, it has to be in kilograms per mole. All right, so let's get a little more into this idea of different molecules having different speeds, and we'll actually pull up a plot here. So this plot is what's called a Maxwell-Boltzmann distribution. It's the type of plot we use when we're trying to measure something like the speed of our molecules, and there's more than one correct answer, right? In this case, we have a bunch of different molecules with a bunch of different speeds. So I have on the x-axis here the molecular speed, and then on the y-axis I have the number of molecules at that speed. So if I look at a low speed down here, I only have a few molecules at that speed. If I increase the speed a bit, I get a lot more molecules at a given speed. So right here in the middle of this hump, this is our most probable speed. And then you'll notice that our root mean squared speed is a little higher than our most probable speed. And in between those is our average speed. So it turns out the average speed is not the same as our root mean square speed, which you probably could have guessed. And the reason we then have to use this RMS speed instead of the average is because if we use the average here, then this equation actually doesn't stay as simple. It gets more complicated. So it seems a little counterintuitive. We use this really complicated calculation to simplify our equation, but that's actually exactly what we're doing. Let's practice with this equation real fast. Let's go ahead and calculate the speed of N2 molecules at room temperature. So this is just the nitrogen in the gas or in the atmosphere around us. So the vast majority of the atmosphere is made out of nitrogen. So this is an important molecule, but let's go ahead and calculate its RMS speed. So we're just going to take this equation, 3RT over M. We're going to plug in R here, which is 8.3145 joules per Kelvin per mole. And I'll make a point here about joules. So if you'll remember, the joule is equal to kilograms times meters squared divided by seconds squared. And so since joules is equal to this kilogram, that's why we have to have our molecular weight in kilograms as well, so that the 2 kilograms can cancel out. So then how do I get my molecular weight in kilograms? Well, I'm looking for N2. So nitrogen by itself weighs 14 grams per mole. We have 2 nitrogens here, so we're going to take that 14 times it by 2 to get 28 grams per mole. Then divide that by 1,000 to get 0.028 kilograms per mole. And then our temperature here, why did I use 298.15 when there's actually no temperature given in the question? Well, what I do say is at room temperature. So what does room temperature mean? Well, if you remember from the beginning of the semester, room temperature means 25 degrees Celsius. It's not the actual temperature, whatever room you're in, you're not going to measure it. So scientifically, we define room temperature as 25 degrees Celsius. I don't know how many rooms are actually at 25 degrees Celsius. It seems like a small number. But so we'll take 25 and we'll add 273.15 to convert it into Kelvin. Then we plug all this into our calculator and find that nitrogen, its root mean squared speed is 515 meters per second. Right, so that's a little bit higher than our average speed there, but it's still a really big number. To put that in context, the speed of sound is 343 meters per second. So what we're saying is that on average, these nitrogen molecules are bouncing around at speeds faster than the speed of sound. Of course, they're all bouncing into each other, and there's a lot of them, so they don't move very far very quickly. They just kind of bounce back and forth and slowly drift around as they hit everything. But right now, molecules are hitting your face at faster than 500 meters per second. And to convert that into another unit, one that you're probably more familiar with, that's equal to about 1,152 miles per hour. So these are very fast gas molecules zooming around. Yes, molecules are very active, moving very quickly. So let's keep playing with this equation though. Let's look at this equation and how our speed is affected by temperature. So how does the temperature of the gas affect the speed of the gas molecule? Now, if you'll notice here in the equation, the temperature is in the numerator. So in other words, as temperature increases, our speed should increase. So here I have a plot where on the x-axis, I have my speed in meters per second. On the y-axis, I have my number of molecules. And then each of these curves then corresponds to a different temperature. So I have my blue curve corresponding to 100 Kelvin, and my green curve's 300 Kelvin, 500, 1000, etc. Okay, so what's going on here? Well, let's first look at this 100 Kelvin curve. You'll notice that it has this most probable peak somewhere around, I don't know, about 250 meters per second. But even as we heat this up, you still have some molecules at 250 meters per second. Even if you go up to 1000 Kelvin, so increase the temperature tenfold, you still have molecules at these lower speeds. Well, what is happening is kind of like you're putting your hand on the top of this peak and smushing it down, right? So as we increase the temperature, there's two things that are happening. One is that we're getting an average, or that the average speed is getting higher. So the most probable speed here at the middle is increasing, which means that the RMS speed is also increasing. And the distributions of speeds that we're getting are also getting wider, right? So at low temperatures, we have this narrower peak, and at higher temperatures, we have this broader peak. Another way of thinking about this is as we increase temperature, we're increasing the amount of available speeds the molecules can have. And then they get kind of randomly assorted into those different speeds. Now let's talk about speed and mass. So if you'll notice from the equation, the mass is on the denominator for the speed, which means that as mass increases, we're going to get a slower speed. So right here, I have another one of these plots where I have the speed on the x-axis and the number of molecules at that speed on the y-axis. And then I have these different curves corresponding to different gases, all at the same temperature. So I have one for hydrogen gas, helium, water, nitrogen, and oxygen. Which curves correspond to which species? Well, we're actually going to order these in terms of increasing weight from right to left. Or in other words, this really broad peak, the one with the highest root mean speed, is going to be H2 gas, which has a mass of 2. Then comes helium, which has a mass of 4. Then comes water, which has a mass of 18. Nitrogen has a mass of 28. Oxygen has a mass of 32. Just to help illustrate this point, I have some more simulations here. On the left is a simulation of hydrogen gas molecules, and on the right is a simulation of oxygen gas molecules. So these are simulations performed using real kinetic molecular theory parameters. They're done at the same temperature. I simply change the mass of the molecule I'm simulating. And what you'll notice, right, is that these hydrogen molecules are on average moving much more quickly than these molecules of oxygen. So the takeaway is the bigger something is, the slower it's going to move. The heavier something is, the slower it's going to move, right? If you're trying to make a car go faster, you got to strip off as many heavy parts as you can and make it as light as possible so that it can go faster. And it's the same idea here. The lighter things move more quickly, heavier things move more slowly. So let's see how you're doing with this idea. Here I have our root mean square speed equation still. And I want you to tell me if I have a mixture of N2, O2, argon, CO2, and H2O, all at similar concentrations at the same temperature, which of these is going to have the greatest root mean squared speed? Go ahead and pause the video and try and figure that out. All right, the way you should be approaching this is by looking at these different gases and figuring out what they weigh and how that affects their speed. So N2 weighs 28, so nitrogen weighs 14 times 2 is 28. Oxygen weighs 16 times 2, which is 32. argon weighs 40, CO2 weighs 12 plus 16 times 2, so that comes out to be 44, and water down here is 2 plus 16, which would be 18, right? So that's again 28, 32, 40, 44, and 18. The lightest of those is going to be the fastest, right? You're going to be dividing by the smallest number. And so our fastest, or the molecule or component with the greatest RMS speed, is going to be water. We'll try that one more time, but this time, tell me which of these molecules is going to be the slowest. Go ahead and pause and try and figure that out. All right, in this case, it's going to be the reverse, right? It's going to be our heaviest molecule is going to be the slowest, whereas in the previous, our lightest molecule was the fastest. So again, the masses here are 28, 32, 40, 44, and 18. So CO2 is our heaviest species. It's going to be our slowest. Let's move on to some new terms here. The terms effusion and diffusion. So diffusion is a term that most people are familiar with, or most people have at least heard, whether or not they understand it. And then effusion is a word that most people have not heard before taking a class like this. Let's start with the more familiar diffusion term. So diffusion is just the spreading out of a gas into its container. So this could be like if you open a tank of helium in a room, that helium, right, is then going to diffuse throughout the room. It's going to spread out as much as it can to fill its container. Effusion is similar, except effusion is talking specifically about the part where the gas is going through a tiny hole. This is actually also happening if you open a gas cylinder, right? If you open a gas cylinder, now all the gas is going through a tiny hole in that cylinder that's letting all the gas out. So effusion is gas moving through a hole where you have a higher concentration of the gas on one side than on the other. So the gas is trying to move through the hole so that it's properly spread out and properly diffused. Now, in both of these, we're going to be concerned about the RMS velocity of our molecules. And the RMS velocity is going to help determine how quickly a gas will diffuse or how quickly it will effuse through a hole. But these ideas here are actually pretty complex, and they could make up a whole course on their own. So we don't actually learn all the complexities of diffusion and effusion in Chem 105. What we are going to focus on is this fact right here, that both of these are going to depend on the root mean square or speed, and that's going to be proportional to 1 over the square root of the molecular weight. As you can imagine, a gas effusing through a tiny hole, obviously the faster the molecules are moving, the faster they're going to move through that hole, but the rate at which the gas moves from one side to the other, or how long it takes for a certain number of moles to move from one side to the other, is going to depend on the size of the hole there. It's also going to depend on what other gases are present. So if this is a high pressure system and I'm trying to release a high pressure gas into a high pressure room, then that's going to be slower than if I'm in outer space and open gas tank. And similar considerations come into place for diffusion, right? A gas can diffuse much more quickly if it's in a low pressure environment where there's not as many other molecules to bump into and bounce around into. And so if it's a high pressure environment, diffusion happens more slowly. Anyways, let's move past that though and just focus on the fact that these both depend on 1 over the square root of the molecular mass. So this was first noticed by Thomas Graham back in the early 1800s. And Graham came up with this idea that the rate of effusion or the rate of diffusion is proportional to 1 over the square root of our mass. And our rate here is defined as moles per second. So the moles per second that are effusing or diffusing, etc. And his actual law, he just took this equation written right here and divided it by itself. In other words, he said the rate of effusion for gas A divided by the rate of effusion for gas B is equal to the square root of the molecular mass of the gas, or gas B, divided by the molecular mass of gas A. So in Graham's law, this describes effusion and diffusion of gases. It doesn't actually give us a way of calculating exact rates of these species, but it can tell us which rate is going to be greater and by how much. So if we know the rate at which one gas is diffusing, then we will be able to figure out the rate at which another gas is diffusing. All right, let's see how you're doing with this. Let's pretend I have 3 balloons. One is filled with hydrogen gas, one with nitrogen gas, and one with SF6 gas. Let's say that these all have the same volume of gas at the same temperature, so they all have the same number of moles as well. And then let's say that I open these balloons out and let the gas escape. Which one of these will deflate first? The hydrogen balloon, the nitrogen balloon, or the SF6? Go ahead and pause the video there and try and figure it out. All right, well, we said effusion, the rate of effusion is inversely proportional to 1 over the square root of molecular mass, which means that the heavier something is, the slower the gas is going to effuse out of the hole at the bottom of the balloon. Which means the one that's going to deflate first is the one where the gas molecules are coming out the fastest. And that's going to happen for our lightest gas, which is H2. Okay, so the answer here is H2. Let's now practice with some numerical calculations here with Graham's law. Let's say we have a gas cylinder and it has a tiny hole in it. And it takes 54 minutes for 0.01 moles of helium to leak out of that cylinder. If the cylinder is then refilled with argon, how long would it take for 0.01 moles of argon to leak out? Well, for this, we're going to turn to Graham's law. And Graham's law is just that the rate says that the rate of helium diffusing divided by the rate of argon diffusing is going to be equal to the square root of the molecular mass of the argon divided by the molecular mass of the helium. And then the term rate here, or the word rate, specifically means the number of moles of helium that are going to be effusing over a given time. So we have moles divided by time substituted in for rate. You'll notice we did this twice, so we have moles of helium and moles of argon, time of helium and time of argon, right? And the reason that the rate for argon over here is flipped over, so the reason we have time on top and moles on the bottom, is because on the left of this equation, we're actually dividing by the rate of argon diffusion. So now we need to solve this equation. And what are we looking for? Well, we're trying to figure out the amount of time it's going to take for argon to deflate. So we need to divide over by the time of helium and divide out the number of moles of helium and also move this number of moles of argon over to the left. Basically, we need to move everything. Now, in this specific problem, we have 0.01 moles of helium and 0.01 moles of argon. So we actually get to cancel those two out simply because they are the same number. If they were different, we wouldn't get to do that. But since we get to calculate those out, we can rearrange this equation so that it just looks like this. Our time of our argon effusion is just going to be equal to the time of the helium effusion times the square root of the molecular mass of argon divided by the molecular mass of helium. If we then plug in numbers there, we said it took 54 minutes for the helium to leak out. The mass of argon is about 40 grams per mole, and the mass of helium is about 4 grams per mole. And so that is going to work out to be about 171 minutes or 2 hours and 51 minutes for the argon to totally leak out. In other words, that's about 3 times longer than it took for the helium, even though the mass of argon is 10 times greater. The reason that we're not getting a linear relationship, right, is because we have this square root. So if you increase the mass tenfold, then you're really only increasing the the effusion rate, or decreasing the effusion rate by a factor of the square root of 10, which is about 3. All right, let's see how you're doing with this idea. I want you to list the following gases, all at the same temperature in order of increasing rates of effusion. And you're going to need this equation right here to do that. Go ahead and pause the video now and try and figure that out. All right, again, the idea here is that heavier things effuse more quickly, lighter things effuse less quickly. Now, one thing that does trip a lot of people up is this phrase, in order of increasing. So in order of increasing means that the slowest should be at the, or the lowest should be at the left, the highest should be at the right. So here, let's figure out which our slowest will be, which will be our heaviest gas, and that'll go on the left. So helium weighs 4, krypton weighs, what is it, it's like 78 or somewhere around there. Nitrogen monoxide is 14 plus 16, so that's 30, and then O2 is 16 times 2, so that's 32. So krypton here is going to be our heaviest. Ideally, you would have looked at a periodic table and figured out its actual rate. But krypton's the heaviest, followed by oxygen, then nitrogen monoxide, and lastly helium. So our answer here is going to be C. All right, so we've spent a lot of time talking about speeds and rates. Now let's talk about one last thing, which is pressure. So pressure is the amount of force applied to a given area. So one common unit of pressure is pounds per square inch. So atmospheric pressure is about 14 pounds per square inch, which means that every inch of skin on your body is being pushed on with a force of 14 pounds. So it's like having 14 pounds on your face. So there's 14 pounds per square inch. Now, the reason you don't feel like somebody really heavy is sitting on you is because your body is also exhibiting a force or a pressure outward of about the same amount. But what is this pressure being caused by on the molecular level? Why do we have a pressure? Well, pressure is just impacts between molecules. So the pressure that you feel on your face, or in a, let's say you get in a pool and you go underwater and you start feeling that pressure on your ears, that pressure is just gas molecules hitting into you. So the more gas molecules you have hitting into you, or the more velocity or speed that you're getting hit by these molecules, the greater pressure, right? So there's two things that can increase it. One is an increased number of collisions, and two is higher energy collisions. Right, so then atmospheric pressure is just the pressure of air per unit area. So how do we measure pressure? Well, the first way of measuring pressure was with a barometer that looked like this, where you'd have a bowl, and the scientists would actually fill the bowl with mercury, and then they'd take a glass column or glass tube, and they'd suck all the gas or air out of it, and then they would stick it into this bowl. And then the mercury would climb up this column. Well, it's a common mistake for new students to think that the vacuum is pulling this mercury up. Let's think about that, a vacuum pulling. What in the vacuum would actually be doing the pulling? There's nothing in there to be exerting any, or that's exerting any forces on the mercury. If there was, then empty space or outer space would be full of force that's pulling everybody, and it would, there's a lot of empty space, so it could almost rip the universe apart, right? Rip everything to shreds. But that's not what's happening. There's a vacuum there, which means there's nothing there. There's no force being applied. There's no pulling being done. So why is the mercury moving up here? Well, the mercury is moving up because there's atmospheric pressure pushing down on the mercury here. But then why does the mercury stop moving up? Well, it turns out that the height to which this mercury goes up actually depends on the balancing of two forces. The first is gravity, right? So gravity is pulling this mercury down, and if you can imagine, if you double the amount of mercury in this column, you're going to double the amount of gravity pulling it down. The other force is what we've already talked about, is this atmospheric pressure pushing on the mercury here, trying to just push it. And because it's pushing it and there's nothing in this vacuum pushing back, the atmosphere is actually able to push that mercury in there. So then the mercury will keep going until the height, or the amount of mercury in here getting pulled down by gravity, is equal in force to the amount of pressure being exerted by the atmosphere. Right, and so a lot of people ask, why do we use mercury for this? Well, it's because it's a heavy liquid. So that means that we're not going to have to push it up super far before the force required to push it up is balanced by the force of gravity. And it's a liquid, which we need, but it's also fairly inert. It doesn't evaporate. So if we have this sitting in a reaction vessel, we don't have to worry about the mercury evaporating into the air and then settling onto our reaction. It also doesn't absorb things very well. So if we're creating a gas or we're having a reaction between gases, we don't have to worry about those going into mercury a ton, right? And so mercury is just a convenient choice for this. It also isn't evaporating, right? You wouldn't want to use something like water for this, especially in a hot reaction where the water is going to be boiling away, and then you don't know anything. So we measure, though, the height of mercury here, usually in millimeters, and the height then is related to our pressure. It's directly related to our pressure. And so we say that 760 millimeters of mercury, or it's been measured that 760 millimeters of mercury is equal to 1 atmosphere of pressure. So an atmosphere is another metric for measuring the pressure, and 1 atmosphere is just equal to the pressure of our atmosphere at sea level. So if you take one of these down to sea level, the mercury generally rises about 760 millimeters. All right, so this is the barometer. Another type of pressure measuring technique or device is called the manometer or manometer. Well, the manometer works in a fairly similar way, except in this case, you have your mercury sitting in this little elbow right here. And the idea is that if you have pressure changes in your vessel, this mercury will move, right? If you have a reaction that lowers the pressure in this left side, then you still have atmospheric pressure pushing down on this mercury, but now you've reduced the amount of pressure inside your vessel pushing down on mercury. So you're going to get an imbalance, and the mercury is going to move up somewhat until the force of gravity overcomes the difference in pressure. Similarly, if you build up a lot of pressure, you can imagine that the pressure is then going to move the mercury the other way. So this is what we call an open manometer, because one tip or one side is open to the atmosphere. So in these open systems, right, if you get a delta H, or a change in height or difference in height between the left side of this and the right, in other words, if your mercury goes down on the outside, and then of course that means you have lower pressure on the inside. Anyways, you can also make these manometers with a closed end. So in this case, you have a set amount of gas in here, and often this will either be set at a specific pressure or it'll be evacuated depending on the type of manometer you're using. But again, the idea here is pretty similar. As you increase pressure in here, it's going to push on this mercury, but now you're actually compressing a gas, and so as that gas compresses, it's going to exert a greater force. And in a closed manometer, your delta H, or your difference in height, is then directly related to your pressure inside your system. All right, we're going to finish off really quickly just talking in units of pressure. So I've mentioned 2 so far. The first is the atmosphere. So an atmosphere is the pressure of the atmosphere at sea level, and that's of course equal to 760 millimeters of mercury. So that's how high mercury will rise. I'm really happy that this experiment resulted in a really round number, because if we look at pounds per square inch, which is the common unit in the United States. 1 atmosphere is equal to 14.696 psi. It's just not a very straightforward conversion. And then occasionally you'll have some jerk that'll report something in inches per mercury. They'll convert from millimeters to inches, and that's 29.9 inches of mercury, which I'll point out here is a little over 2 feet. So the mercury, these barometers, have to be fairly tall to measure that many millimeters of mercury. Now, actually, none of these are the SI unit, the standard unit, though most scientists nowadays use the atmosphere. The recommended unit is actually the Pascal, named for Blaise Pascal, the guy that came up with it in the early 1600s. So people have actually been measuring pressure for a long, long time. And 1 atmosphere is equal to 101,325 pascals. So the Pascal almost seems like just some random number. We'll often also use kilopascals because that's just 101 kilopascals per atmosphere. But the Pascal is not a very useful pressure, a unit of pressure. Sometimes we'll use the bar, which is exactly 10 to the 5th pascals. So you'll notice 1 atom is 1.01325 times 10 to the 5th pascals. So an atmosphere and a bar are actually very close together. I like the atmosphere better, but actually in my lab, a lot of our equipment is built to measure in bar and specifically in millibar. So in my lab, we go to low pressures. We actually go to super low pressures, so 10 to the negative 12th millibar. But anyways, so the atmosphere and the bar are roughly the same. The bar is just about 1% less than an atmosphere. So there's a whole host of units for atmosphere. For pressure. I wish there weren't, but that's the situation we're in. We'll finish off with just an eye clicker quiz. And a mercury barometer, the mercury is A, pulled up the tube by the vacuum at the top, B, pushed up the tube by the weight of mercury at the base, pushed up the tube by the pressure of the air, D, pulled up the tube by the second law of thermodynamics, or E, none of the above. Go ahead and pause the video and try and figure that out. And hopefully you got C. It's pushed up the tube by the pressure of the air. All right, let me know if you have any problems with that, and I will be glad to help you out.